In this hour, we study Lyapunov test for controllability, and later on we will talk about an application of that test. This is the theorem that's also known as the Lyapunov test for controllability. Okay, so consider the following system: x that equals ax plus bu. Okay, our LTI system, and we're going to assume that this system is exponentially stable in the sense of Lyapunov. Okay, suppose so. Let the system be exponentially stable. Okay, in other words, all the eigenvalues of the A matrix are with strictly negative real parts. Then this system is controllable if and only if we can find a symmetric positive definite matrix, okay, P, that solves the Lyapunov equation given below. The following Lyapunov equation. Okay, AP plus PAT equals minus BB transpose. Okay, A is the system matrix and B is the control matrix. Okay, furthermore, the theorem tells us how to construct such P. Okay, this P is unique and can be constructed through the following integral. P equals from 0 to infinity e to the A transpose B transpose e to the A transpose T dt. Okay. Now we're now gonna prove this interesting claim, okay, known as the Lyapunov test for controllability. Note that we'll be working under the following assumption, that our system is exponentially stable. Okay, so we're having a controllability result for a special type of LTI system, that is an exponentially stable LTI system. Okay, so let's begin our proof. Okay, part 1, we're going to show that if AB is controllable, then the claims concerning this matrix P hold, and then we will show the reverse direction. That is, if we have such a P, then the system must be controllable, or the pair AB must be controllable. Okay, part 1. Let the system or the pair AB be controllable. Okay, that is, the controllable matrix is of rank n being the order of our system, or there exists no eigenvector of the matrix A transpose that belongs to the null space of B transpose. That was our PBH test for controllability. Okay, so to prove the claims regarding this symmetric positive definite matrix, we have to answer certain questions, such as, does P, okay, where its construction is given here, 0 to infinity e to the A T B transpose e to the A transpose T dt satisfy the Lyapunov equation. Okay, so we have to prove this. We have to also show that P is unique. Okay, those are among the claims of our theorem. And then we have to show also that P is positive definite. Okay, is P positive definite. Okay, now the how to prove these two parts, or how to show that the answers to those questions are yes. Okay, we can use the methods that we employ when showing the similar parts of the proof of the Lyapunov theorem for exponential stability. Okay, so since showing these parts and those parts are very similar, we're gonna skip showing these two pieces. Okay, and we're gonna continue directly with the third question, whose answer hopefully will turn out to be yes as well. Okay, so these parts are left as an exercise, or if you don't have time, you can check the text. But as I said, it's showing them is very similar to the parts that we showed. Where parts, I mean the parts that are similar to in the theorem of Lyapunov test for exponential stability. Okay. Now let's show that P is a positive definite matrix. Okay, so suppose not. So we're going to show by contradiction. Suppose that P is not positive definite, then we can find a non-zero vector in Rn. Okay, and n is such that it's the and A is an n by n matrix, or n is the order of our system. So we can find a non-zero vector x such that x transpose px is 0 or something negative. Okay, if you can find such an x, so that means P cannot be positive definite by definition of positive definiteness. Okay, so since P is given by this integration, let's apply that construction to this inequality, and then what we have is the following: from 0 to infinity. Since x is a constant vector, we can put it inside the integration, and we can write x transpose e to the a t b b transpose e to the a transpose t x dt. And that, since that's something transpose times the same thing, okay, we can write it as the norm square of something. So that implies that this integral, okay, b transpose e to the a transpose tx squared dt is less than or equal to 0. Now, what's happening here is we are integrating something, okay, the norm square of something, therefore this is never negative, and the result of the integral is less than or equal to 0. Since this is never, the integrand is never negative, the integral can be never negative, therefore this being less than or equal to 0 means that this thing being integrated must be 0, okay, identically 0. Since this is norm squared, the norm is 0, and since this, if the norm is 0, the thing inside must be 0 for all times, and since the thing inside is 0 at all times, it means its transpose is also 0 at all times. Hence, that implies that X transpose e to the AT times B, which is the thing inside the norm transposed, equals 0 for all times. Okay, so once again, if P is not positive definite, then this thing must be 0 for all times for a non-zero vector X. Okay, and from that equation, we will now show that the pair AB cannot be controllable. And since the pair AB is controllable, that's our starting point, we will have reached a contradiction which would give us that P is a positive definite matrix. Okay, so since that's 0 for all times, clearly it's 0 at t equals 0. So X transpose e to the AT times B evaluated at t equals 0 equals 0. Then what? If this is 0 at all times, its derivative must be 0 at all times too. Okay, so let's also do that, d over dt. X transpose e to the AT B. Okay, you evaluate this derivative and then compute this derivative, then evaluate that t equals 0. Okay, t equals 0, that must be 0, and so on up to the n minus first derivative. X transpose e to the AT B at t equals 0 must be 0. Okay. Now at t equals 0, e to the AT is identity matrix. Therefore, this yields X transpose B equals 0. Then let's look at the second equation. The derivative of this, the only time varying term is e to the AT. Its derivative is a times e to the AT. So here we have X transpose a times e to the AT times B. We're evaluating that at t equals 0. At t equals 0, e to the AT is identity. So what we have is X transpose times A times B equals 0. X transpose A, B equals 0. Differentiating it once again produces A squared. Then furthermore, once again more than you will have A cubed and so on. So you go up to n minus first power of A. Okay. So what we have is X transpose A raised to the power n minus 1 times B equals 0. So what we have obtained is these n equations. Now, let's collect all those n equations in a single equation. Okay, so let's do that. And we can write X transpose times B, AB, A n minus B equals 0. Okay, so this single equation is all these n equations written in a compact way. Now, when you write all these n equations in this form, we immediately recognize that the controllability matrix appears. Okay, so that means, so this is our C matrix. So that means rank of the controllability matrix, since X was a non-zero vector, so that means the rows of this matrix, the controllability matrix, must be linearly dependent. It has n rows, okay, because system is of order n. That means rank of C cannot be n. Okay, and then we know that whenever the controllable matrix is not full rank, the system is not controllable. Okay, And that means, because that was our starting assumption, that means we have reached a contradiction. Okay, therefore, this P satisfies the Lyapunov equation. It's unique. Well, those parts we didn't show, but they're easy to show, similar to an earlier proof. And then we have shown also that P is positive definite. Therefore, part 1 is complete. That is, if for an exponential system, although we didn't use for an exponential stable system, x equals ax plus bu, if the pair AB is controllable, then a P symmetric positive definite matrix must exist, which satisfy the following conditions. Okay, now let's move on to part 2, where this time we will start with a P satisfying these properties, and from that we will establish that the pair AB is controllable. Part 2. Suppose that we have a symmetric positive definite matrix satisfying the Lyapunov equation for controllability. Okay, AP plus PAT equals minus BB transpose. And remember that we're always working for this theorem under the condition that the system is exponentially stable in the sense of Lyapunov. That is, all the eigenvalues of A are with negative real parts. Okay, has a symmetric positive definite solution. Okay. Now, suppose that X is an eigenvector, or pick an eigenvector of the matrix A transpose. Okay, so let X be an eigenvector of A transpose. Okay, if you can show that that vector can never be in the null space of B transpose by PBH test, we will have shown that system is controllable. Okay, so let's proceed then. That is, A transpose X equals lambda X for some complex, possibly complex scalar. Okay, for some lambda in C. Now, lambda is the eigenvalue of A transpose. Okay. Now, A transpose and A, they have the same eigenvalues. Okay. And then we're working under the assumption that the system is exponentially stable. Therefore, all the eigenvalues of A are with negative real parts. Therefore, all the eigenvalues of A transpose are with negative real parts. Hence, the real part of lambda, whatever it is, must be negative. Okay. So let's proceed then as follows. We write the following: B transpose X norm, and then we take the square. Okay. X is this eigenvector. Now this can be written as minus X conjugate transpose B transpose X. Okay, so by definition of Euclidean norm. Here X conjugate transpose is denoted by this X star. Okay. Conjugate transpose of X. Okay, because possibly X is a complex vector. Okay, then since minus BB transpose equals AP plus PAT, we can replace this minus BB transpose by the left-hand side of the Lyapunov equation, and that yields x star times AP plus PA transpose times x. Okay. And that reads what? X conjugate transpose times A Px, and then here we have X conjugate transpose PA transpose X. Now X conjugate transpose A can be written as A conjugate transpose times X, and then you take the conjugate transpose once again. So what we have therefore here is A conjugate transpose times X, then conjugate transpose once again. But since A is real, it's conjugate transpose, and it's transpose, it's the same thing. Therefore, we can use this more familiar notation for A. Okay, so X conjugate transpose is this: A transpose times X cis conjugate transpose. And then we have P, and then we have X coming from the other side. Plus X conjugate transpose P, and here we have A transpose X. Okay, now what's A transpose X? It's lambda X, because X is an eigenvector of A transpose. So let's therefore rewrite those terms, A transpose X, by lambda X. So what we have here is lambda times X conjugate transpose, and that's lambda conjugate X conjugate Px plus, here we have A transpose X, that's lambda X. Lambda is a scalar, therefore we can carry it wherever we want. And here we have lambda and X conjugate transpose Px. Okay. So here we have X conjugate Px, and here we have X conjugate transpose Px again. And therefore, we can write this as lambda star plus lambda times X conjugate transpose Px. Now, lambda conjugate plus lambda clearly is 2 times the real part of lambda. So here we have 2 times the real part of lambda times X conjugate transpose Px. Okay. Now, X is an eigenvector, therefore it's non-zero. P is a symmetric positive definite matrix, therefore by definition X conjugate transpose Px must be a positive real number. Okay, so here we have positive real number. And then this thing is, because A is exponentially, the system is exponentially stable, this thing is negative. Okay, negative real, therefore negative times positive gives us a negative, and here we have another -1 here, negative. Therefore, multiplying both sides with -1 produces that B transpose X norm squared is something positive. Okay, so and that means B transpose X is non-zero, and that means X cannot be in the null space of B transpose, and that was what we wanted to show. Finally, A exponentially stable, okay, or X that equals AX plus BU exponentially stable implies that the real part of lambda is strictly negative, and that yields that B transpose X norm must be positive, because here we have negative, here we have another negative, and then we have the positivity of the norm. And that means what's being normed is non-zero. B transpose X is different than 0. Okay, so all that remains is to combine that X, which is an eigenvector of A transpose, cannot be in the null space of B transpose, and from the PBH test we know that that immediately implies controllability. AB controllable. Okay, so that's the end of our proof. Note that all these implications are reversible. Okay, so if you have such a P satisfying certain properties, then starting from the fact that AB controllable, you can reach that A is exponentially stable. And that means that we have also unintentionally proven the following sister theorem. Okay, in the theorem that we started with, we just proved our assumption that our assumption was that the system is exponentially stable. This time our assumption will be that AB is controllable. Okay, so under this condition, the fact that that the pair AB is controllable, we have the following equivalence. Then A is exponentially stable. Well, this just means, this is just an informal way of saying that the system x that equals ax, or x that equals ax plus bu, is exponentially stable in the sense of Lyapunov if and only if, okay, A is exponentially stable if and only if the Lyapunov equation AP plus PA transpose plus B transpose equals 0 has a symmetric positive definite solution. Okay, so that's the, in a sense, the dual theorem. And now what we will do, we will talk about an application of this Lyapunov test for controllability on constructing a state feedback to stabilize the origin of a controllable system. Here is an application of the Lyapunov test for controllability. Okay, now what we want to do is, using the Lyapunov test, we want to construct, suppose, a state feedback law under which the origin of the system becomes exponentially stable. Okay, so we start with, therefore, a controllable system. Given a controllable pair AB, before we apply the Lyapunov test, let's make the following observations. Observe the following. Okay. First of all, for a real number, okay, a real scalar mu, pair minus mu I minus A, comma B. Okay, now we can consider this as A tilde, which we construct from A and mu as follows: minus mu times identity matrix minus A. So this is a new matrix, and then, or we can call it A tilde, and B tilde is same as B. Okay, and now this new pair is also a controllable pair. Okay, that's the first observation that we need to make. A pair minus mu I minus A comma B is also controllable. Okay. Why is that? Well, it directly follows from the eigenvector test. Okay, it's very easy to show it with the eigenvector test, because of the following. Now, if this system is controllable, then it means by PBH test no eigenvector of A transpose belongs to the null space of B transpose. And now, if V is an eigenvector of A transpose, then automatically it's also the eigenvector of the transpose of this matrix, and then that vector is not in the null space of B transpose, and here we have the same B matrix. Therefore, whenever this pair is controllable, then and only then this pair is also controllable. Okay, so let's put that down. A transpose equals lambda V implies that minus mu I minus A transpose B equals minus mu minus lambda V. Okay, so this means if V is an eigenvector of A transpose with the corresponding eigenvalue lambda, then that same vector is also the eigenvector of this matrix transpose with the corresponding eigenvalue being minus mu minus lambda. Okay, and PBH test. So the controllability immediately follows from the PBH test. And the second observation that will be useful for our eventual construction of the state feedback. Here is the second observation. By choosing large enough mu, okay, we can always make the matrix minus mu I minus A exponentially stable. In other words, we can make it such that all the eigenvalues of this matrix are on the open left half plane for all eigenvalues. Okay, this is clear from the fact that the eigenvalues of minus mu I minus A matrix are here, minus mu minus lambda, even though this can be something quite with a positive real part, and that real part could be very large. By choosing mu even larger, we can carry everything, okay? We can push everything to the left of the complex plane, therefore make the eigenvalues, all the eigenvalues of this matrix with negative real parts. Okay, so those were very simple observations, and they will be of key importance for our construction. Now, we proceed as follows. Okay. Given a controllable pair AB, what we do is, the first step, we choose this real number mu. Okay. Large enough so that minus mu I minus A is exponentially stable. Okay. In other words, this matrix is with eigenvalues that are all with negative real parts. Such matrix is also sometimes called Hurwitz. Okay, so that matrix is Hurwitz. Okay, then since this matrix is Hurwitz or exponentially stable, and the pair that and B is controllable, we can apply Lyapunov test for controllability, and which tells us that minus mu I minus A times the matrix V plus V minus mu I minus A transpose equals minus B transpose. Okay, so this equation has a symmetric positive definite solution V, okay, from the Lyapunov theorem for controllability. Has a solution V symmetric and positive definite. Okay, so it's V is an n by n matrix where n is the order of our system. Okay, now what we do is we rewrite that equation in the following way: A V plus VA transpose minus B transpose equals minus 2 mu times V. Okay, all we did is reorganizing the terms. We have minus AV here, minus VA here. We carry all those guys to the other side, and what remains is what remains here on the left hand side is minus mu V and another minus mu V, so that makes minus 2 mu V. Okay, and then we multiply both sides of this equation by the inverse of V, okay, which we call P. Okay, so let P be the inverse of V. Since V is symmetric positive definite, its inverse is also symmetric positive definite. So by multiplying both sides with P, what we have is P times AV plus VA transpose P equals minus 2 mu PVP. Okay, and then that produces what? Okay, so what we have is PAV, and then a P is coming from the right hand side. V times P is identity matrix because they are the inverses of one another. So here this produces PA, and then this P cancels that V, okay, because they are inverse of one another, plus A transpose P. Finally, we have this term multiplied from left and right by P, okay, minus PBBT. And how about the right hand side? Okay, V is the inverse of P, or P is the inverse of V, therefore this is, one of them is identity. So what remains is minus 2 mu P. Okay, and then by introducing the following matrix, which will be eventually our state feedback law, K defined as 1/2 B transpose times P, we can rewrite the left hand side as follows: P times A minus BK plus A minus BK transpose times P equals minus 2 mu P. Okay, so this is an important form because with that form we're familiar with from Lyapunov test for exponential stability. Okay, now if you name this matrix A tilde, let's say, and if you name this matrix Q, what we have is P A tilde plus A tilde transpose P equals minus Q. Now, this matrix that we call Q is 2 mu P. Mu is positive, P is a positive definite matrix, therefore Q is a positive definite matrix, okay? And P is a positive definite matrix, therefore what we have is P A tilde plus A tilde transpose P equals minus Q. And because P and Q, they are positive definite matrices from Lyapunov test for exponential stability, it must be that this matrix A minus BK is exponentially stable. All the eigenvalues are with negative real parts. Okay. Since P is positive definite because it's the inverse of a positive definite matrix, and mu is a positive real number, therefore mu times P is also a positive definite matrix. By the Lyapunov stability theorem, we deduce that the system x dot equals A tilde, which is our A minus BK matrix times x, is exponentially stable in the sense of Lyapunov. That is, all the solutions converge to the origin in an exponential fashion. This means that, okay, for a controllable system, solving the Lyapunov equation, which we can solve because we have just proved the relevant theorem, we can obtain a matrix V, and then from that matrix we obtain another matrix P by taking its inverse, and from that matrix P and using the B matrix of our system we construct a matrix K, and that K is a stabilizing state feedback, because this closed loop system is obtained when you steer the system, when you run the system under the feedback U equals minus Kx. Okay, this implies that the system x dot equals Ax plus Bu can be stabilized by state feedback U equals minus Kx.